Okay, so moving on to shapes and polarity of molecules. So this is kind of applying everything that we just learned in this chapter. So we learned about charges, how it can affect shape, how they can bond, how it's either like complete grabbing of the bond or sharing those, bonds. And so now we're going to figure out how this affects shape. So in a molecule of methane, which is CH4, the central carbon atom is going to be bonded to 4 hydrogen atoms. And the best geometry for minimal repulsion is tetrahedral with bond angles of 109 degrees. So given the formula of an ionic compound, we're going to learn how to write write the correct name, and given the name of my ionic compound, we're going to write the correct formula. So the Vesper theory, this is the longhand of the valence shell electron pair repulsion theory, or Vesper theory. And this is going to describe the orientation of electron groups around that central atom. And this states that the electron groups are arranged as far apart as possible around that central atom, and therefore stating that the specific shape of a molecule is determined by the number of atoms that are attached to that central atom. Okay, so what are we doing? Predicting shape. In a molecule of carbon dioxide, 2 electron groups are placed around that central carbon in the central atom, which is carbon. Okay, the repulsion is minimized by placing the 2 groups on opposite sides of the carbon atom, giving the molecule a linear or line type arrangement with bond angles of 180 degrees. The shape with 2 electron groups around the central atom is called linear, like a line. Okay, so pretty straightforward. In a molecule of formaldehyde, which is H2CO3, the 3 electron groups are placed around that central atom, which happens to be, again, a carbon, and the repulsion is minimized by placing 3 groups as far apart as possible. And so that would be the bond angles of 120 degrees. So 360 divided by 3 is 120, right? So the shape with 3 electron groups around the central carbon is called a trigonal planar. Okay, trigonal planar arrangement. In a molecule of SO2, the 3 electron groups are placed around that central atom, which is the sulfur, and it is a single bonded O atom, a double bonded O atom, and also a lone pair of electrons. The repulsion is minimized by placing the 3 groups as far apart as possible. And the shape with the 2 bonds, and a lone pair on the central atom is called bent conformation. Now moving on to 4 electron groups. In a molecule of CH4, the 4 electron groups are attached to the hydrogen atoms around the central atom, which happens to be a carbon. Okay, the repulsion is minimized by placing the 4 groups at the corners of the tetrahedron with the bond angles of 109 degrees. The shape with the 4 bonds on the central atom is called tetrahedral. And then again, you can see the different ways that it can be drawn. In a molecule of NH3+, NH3, the 3 electron groups include 3 bonds to hydrogen atoms, and 1 is a lone pair around that central atom, a nitrogen. The repulsion is minimized by placing the 4 groups at the corners of the tetrahedron with bond angles of 109 degrees. And the shape of 3 bonds and a lone pair on the central atom is called a trigonal pyramid, or pyramidal. Okay, trigonal pyramidal. Apparently my tongue's getting tied today. In a molecule of H2O, the 2 electron groups are attached to hydrogen atoms and have 2 lone pairs that are around that central atom, which is an oxygen. The repulsion is minimized by placing the 4 groups at the corners of that tetrahedron, again with bond angles of 109 degrees. The shape of 2 bonds and 2 lone pairs on the central atom is called bent. So here is your lovely summary chart. Okay, I just ordered the book between these last 2 videos because I'm sick of not having the book. So I have a book now coming, hopefully in a week. All right, so anyway, The molecular shapes for the central atoms of 2, 3, 4 bonded atoms, again, linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, right, bent. So you can see the different shapes, the lone pairs, the bonded atoms, the group name, and the electron groups. So our handy dandy little guide to predicting the molecular shape is going to be 1, draw that electron dot formula. 2, arrange the electron groups around the central atom to minimize the repulsion. 3, use the atoms bonded to the central atom to determine the molecular shape. Okay, so let's apply this. So let's predict the shape of H2S. So let's draw that electron dot formula. Let's arrange the electron groups around that central atom to minimize repulsion. So to minimize the repulsion, the electron groups have to have a tetrahedral arrangement. And then we're going to use the atoms bonded to the central atom to determine the shape. So with 2 bonds and 2 lone pairs, so 2 bonds and 2 lone pairs, the shape is going to be bent. So let's apply. State the number of electron groups and lone pairs and use the Vesper theory to determine the shape of the following molecules as or ions as tetrahedral, trigonal pyramidal, or bent. All right, so pause me and come back. So first what we're going to do is draw that electron dot formula. Okay, so we have 1 central phosphate, right, and 3 Fs. We have 1 central S, 2 hydrogens. We have 1 central carbon, 4 chlorines. All right, and then we are going to arrange the electron groups around the central atoms. So to minimize repulsion, the electron groups have to have a tetrahedral. To minimize repulsion, the groups have to have a tetrahedral. And then to minimize repulsions, the electrons have to have another tetrahedral arrangement. So step 3, use the atoms bonded to the central atom to determine the molecular shape. So with the atoms bonded to the central atom, okay, with 3 bonds and 1 lone pair on the central atom, this is going to be trigonal pyramidal. Let me move out of the way. Okay, H2S with 2 bonds and 2 lone pairs on the central atom, this is bent. With 4 bonds on the central atom, the shape is tetrahedral. Okay. All right, so let's do this with dipoles. And these are non-polar molecules. So such as hydrogen, chlorine, and oxygen. They're non-polar because they contain non-polar bonds. So with polar bonds, they can be nonpolar if the dipoles and the polar bonds cancel each other out in a symmetrical arrangement, such as CO2 and CCl4. So when the dipoles cancel, then you end up affecting the shape. So polar molecules such as HCl are polar because one end of the molecule is more negatively charged than the other, and the polar bonds in the molecule do not cancel each other out. So the electrons are shared unequally in the polar covalent bond. So right here you can see that the single dipole does not cancel. All right. So in polar molecules such as water, there are 2 lone pairs and 2 bonds around that central atom. There are dipoles that do not cancel, therefore they make the molecule positive at one end and negative at the other end. And there is a partial negative charge on the central atom. So the oxygen is going to be the more negative end, so that's why it causes it to kink. And the more positive end is going to be the hydrogens, right? And so H2O or water is a polar molecule because the dipoles do not cancel each other out. In polar molecules such as NH3, there is 1 lone pair and 3 bonds around the central atom. There are dipoles that again do not cancel, and it makes the molecule positive at one end and negative at the other end. And there is a partial negative charge on the central atom. So again, we're going to have the more negative end of the molecule be towards the nitrogen, more positive be towards the hydrogen, and that tells us that NH3 is polar because the dipoles do not cancel out. So our handy dandy little guide to determine polarity is 1, determine if the bonds are polar covalent or nonpolar covalent. And if the bonds are polar covalent, then we're going to draw the electron dot formula and determine if the dipoles cancel. All right. So let's work together to determine if the molecule OF2 is polar or nonpolar. So first, let's do calculations. Okay, so determine if the bonds are polar or nonpolar. Oxygen is 3.5, fluorine is 4. So the difference in that electronegativity number is 0.5. So that tells us that those bonds are going to be polar covalent. If the bonds are polar covalent, then we're going to draw that electron dot formula and determine if the dipoles cancel. So let's draw that out, okay? And we find out that OF2 is a polar molecule, and it's bent. So let's do this as well, and let's identify each of the following molecules as polar or nonpolar. So pause me and come back. All right, how did we do? So identify each. So step 1, determine if the bonds are polar or nonpolar, and then draw it out. So we calculate, okay, P is 2.1, Br is 2.8, so that gives us a difference of 0.7. That tells us that it's polar. Okay, same here is a difference of 0.7. It's going to be polar. This one is a difference of 0.4. That tells us it's nonpolar. So then we draw them knowing that it's polar, polar, nonpolar, and we can see if they cancel each other out or not. Okay, and that wraps up chapter 6 and module 3. Good job, you guys. We'll see you in class.